This video will look at the basic components of the linear model. Many of us may have seen a linear model before. Algebraically, we've probably seen it as one of the three forms that are listed here. So y minus y1 is equal to m times the quantity x minus x1. We may have seen this before, and this is just known as point slope form. Okay. The second form here listed, ax plus by plus c. This is called standard form. Generally, we see this when we're doing system of linear equations. Otherwise, the most common form is this last one, which I have circled, and this is slope-intercept form. This form is the form that we are going to be focusing on for this video. Okay, and so again, recall that m stands for the slope in this particular equation, and then b is the y-intercept. Okay, and then x and y are our unknown variables. So also, we can also think of a linear model graphically. So here I have one such graph. Here's the basic equation of the line, and well, if we note that the y-intercept is b, well, that just means that b is this value on the y-axis that it starts at, or so this function starts at. Okay, so that value is b. Then what we can do is we can look at two different x values, or two different horizontal values. So let's say I have two values here. I'm going to call those a and a1. I'm going to move that one off to the side and this one off to the side for now. So this is a and a1, or a and a plus 1. So if I go up and find those on the function, okay, so I'm going to just kind of trace up to the function. It would hit about there, and again, it would be about here. Okay, so those are where it would intersect horizontally. So if I make a little rectangle, or a little line, horizontal line connecting those two, that horizontal line would look like that. So this would be the change in the x. So I'll just write change in x. Okay. And then vertically, okay, so if I trace over to the vertical axis, or the y-axis in this case, I would find that, well, when I trace over from where a intersects this line of the linear model, that would be f of a, and similarly this would be f of a plus 1. And then the vertical component would be the change, so this part here in purple, that would be the change in y. Okay, just graphically kind of what's going on with a linear model. Okay, and as we progress, so again, y is equal to mx plus c, we talked about b already being the starting value, the y-intercept. In a linear model, we talk about it as, okay, the dependent quantity, so y in this case, is going to start at that value, and then x is going to be our independent quantity. We're going to change that over time, and the other part of this linear model, m, that we know is slope, but how we're going to interpret it in a linear model is that it's going to be a rate of change. Okay, it's going to be a rate of change. Okay, and you can also think of it, if you've studied variation, as a constant of proportionality between the dependent and independent quantity. Okay, if we were to interpret this, the interpretation comes into play in many scenarios. So what we would have to say is that the when we change the independent quantity by 1 unit, okay, then the dependent variable changes by m units. So it's again looking at the slope in a particular context and interpreting it appropriately. Okay, and particularly if we're working in a linear model, the rate of change should either be 0 or constant. So 0, if the rate of change is 0, your model graphically is going to look like a flat line. Okay, so something like that. Constant, it could be going up, it could be going, or the line graphically might be going down. It's going to either rise or fall, okay? And it's going to fall at the same rate. So it's going to, between any two values, it's going to change at the same rate. And then again, just if we need a little bit of a reminder on how to compute slope, it's going to be the difference in the y-coordinates in the numerator over the difference in the x-coordinates in the denominator. And that would be for 2 points x, or x1, y1, and x2, y2. And we're going to conclude this video with a brief example of a linear model. So here I just made this fictitious model. We have 1,000 residents in a city in year 2012. It says, in looking at the population, they determined that it's decreasing. Okay, here's some important information. Decreasing by 150 residents each year since 2012. Okay, so just to answer this first question, so is a linear model appropriate to describe the scenario, why or why not? Well, if I think of this as a graph of time, so maybe this is 2012 at the beginning here, and I know at 2012 the city begins with 10,000 residents. So again, I'm going to make a vertical axis or a horizontal axis as time, and the vertical axis as population. Okay, so 10,000, and then the next year, again, I'm not introducing a scale per se, but in 2013, well, if it decreases by 150 residents each year, okay, at 2013, let's see, this would decrease by 150, so this would be 9850, okay, and so I would have 2 data points here, and then I could continue, say, maybe at 2014, I can look at the population then as well, and this would be at 9,700, okay? And what I can see, and I'm going to use a tool to help me draw a straight line, is I can connect these 3 points, if I drew it correctly, with, they should all lie on a straight line, okay? And then I would, of course, have to draw a little arrow at the end because this model could continue indefinitely according to the scenario. So to answer part A, is a linear model appropriate to describe this scenario? I would say yes, because the population is changing at a constant, okay, that's key here, constant rate or a constant amount, whatever you prefer, each year. Okay, and then, so we've answered part A, and then B says, introduce notation to describe this scenario. Write a mathematical equation describing the rate of change at the end of each year in this problem. So introduce notation, this just means introduce notation for the independent and dependent quantities. So I'm going to define t to be the time in years since 2012, okay? And what this will allow me to do is, on my axis that I have drawn here, 2012 would be equivalent to 0, this would be 1, this would be 2 for 2014, and that just helps me keep the number smaller, okay? And then I'm also going to define my vertical axis, P of t, to be population of the city at t years after 2012. Okay, and so that'll just be my vertical axis up here. Alright, so first part is done, and now I want to write a mathematical equation describing the rate of change at the end of each year of this problem. So in other words, it's asking me, okay, well, what is, so I know that the rate of change is constant. Of change is constant. Okay, so in other words, what it's asking me to find is the value of m. Okay, and we were kind of doing it here, so m is always rise over run, so how far you rise or fall vertically over the horizontal distance traveled. So if I increase 1 year, we said, well, we decreased by 150 people. So I'm just going to say minus 150, and I'm going to add units on this, people per year. Okay, units are generally a very good idea to include whenever you can. All right, and then lastly, part C says write an equation describing the population at the beginning of the city, beginning in year 2012 and continuing t years after 2012. So we know that a linear model applies. So I want to look for something that I can write as y is equal to mx plus b. Okay, now here in our problem, we have to think of our independent and dependent quantities. So how I'm going to translate this is, well, x in this problem is t and y is p of t. Okay, and then we also found that m was that rate of change from right up here. So I'm going to write minus 150. Okay, and then b, if we go back to our linear model when we were talking about the different components and what they represent. This was the starting value, so the city started at 10,000 people in year 2012, and that would be our linear model.